So we are back inside and ready to analyze the data that you have collected outside. So I'm going to talk you through the data analysis that comes with the estimating the size of a population and testing for association between two species. So this was the first set of data that I collected out on my lawn. So I had 0 of this flower, this Bellis perennis, in the first quadrat that I tossed, and 0 in the second, and 5 in the third, and 2, and so forth. So the first thing I do is that I calculate an average. So I found on average 2.6 individuals per quadrat. And so this number I'm going to need a little bit later. Then I also need to make sort of a rough estimate of the total area. Of course, had it been a more proper field investigation, we would have to measure and know the exact area of the site. But I've just made a rough estimate of the total area of my lawn. And the third piece of information that we need to complete this calculation is the area inside the quadrat. And since the quadrat is 15 times 15 centimeters, that is a total of 225 square centimeters, and that's the same as 0.225 meters squared. This also means that I have on average 2.6 individuals per 0.225 meters squared. That is the same as 11.6 individuals per square meter. So an estimate of the total population of Bellis perennis in my lawn is then 11.6, which was the number of individuals per quadrat times per square meter times the 250 square meters that I have in my lawn. So that's 2,900 individuals. So, and again, this is of course an estimate. It's not, I wouldn't necessarily get I probably wouldn't get the exact same number if I went outside and actually calculated each and every one of them. But depending on how many quadrats you toss, you could get a pretty good estimate, right? And of course, the higher the number of quadrats that you toss, the closer your estimate would be to the actual number. So that's a trade-off between how much time you spend and how accurate your results will be. And then for the second part of this sampling, because I also asked you to collect data for conducting a test for association between two species using the chi-squared test. And the chi-squared test is a statistical test that can be used to test, as it says here, if there is a significant difference between expected numbers and observed numbers. It says frequencies here, right? So that's, but do you actually see outside in nature what you expected to see based on some kind of theory? That's what the chi-square can do for us. And it's, as it says down here, it seeks to distinguish between two possibility. So we need two hypotheses for this test. So, and in statistical tests, we always have what is referred to as a null hypothesis. And in this case, the null hypothesis is that there is no significant difference between the distribution of two species. That's the same as stating that the distribution is random. If this hypothesis is not true, then an alternative hypothesis must be true. And in this case, the alternative hypothesis is that there is a significant difference between the distribution of species, meaning that the species are in some way associated. Maybe they prefer to grow apart, maybe they prefer to grow together, maybe they all want to be in the same very sunny spot, maybe they avoid competition with other species. Many different things can come into play when trying to figure out how they are associated. But the test can tell us whether they are associated or not. Yes. So these are the results that I collected. So in 8 of the quadrats that I tossed, I had both species A and species B. In 18, I had no individuals of species A, but I had species B present. In 6 of the quadrats, I had species A, but no species B. And in 42 of the quadrats, I had neither of the two species. So I set this up in the form of a table. So number 8, both present, and here bell is not present, but dandelion present, and so forth. I place it. These are the 4 sort of pieces of data that I have collected, and then I sum up to get the total number of quadrats where dandelion was present, and the total number where dandelion wasn't present, and total number with no bellis, and total number with bellis present. And again, I sum up and I tossed a total of 74 quadrats. And this table now shows my observed frequencies, the observed numbers, the numbers that I have actually counted, and the distribution as it actually is outside. Then we move on to calculate the expected frequencies. And we do that by assuming that the species were randomly distributed. So the theory behind the expected numbers is that they have a random distribution, these two species. So I need my observed numbers to calculate my expected numbers, and I do it like this. So in this cell up here, what I do is that I take the total number of quadrats with dandelion present, and I times that by the total number of quadrats with bellis present, and I divide by the total number of quadrats that I have tossed. And I end up getting a expected frequency of 2.65 for this outcome, bellis present and dandelion present. I do the same for the 3 other cells, right? So here I say, okay, what is the expected frequency of bellis not present but dandelion present? Well, that's the number of quadrats with dandelion present times the number of quadrats with no bellis divided by the total number of quadrats towards the analysis. And it's the same for these 2 cells down here. This gives me up here my observed numbers, down here my expected numbers, and these 2 types of numbers are what I need to calculate what is called the chi-squared value. And the chi-squared value can be, this equation shows how the chi-squared value is calculated. So you sum up observed minus expected numbers to the power of 2 divided by the expected number. And you do that for all 4 cells, right? So for the first cell, this one, I would need my observed number. This would be my O. And then down here, I would have my E, my expected value. So I say 8 minus 2.65, these 2 to the power of 2. And then I divide by the expected number, which is this number down here. So for the first cell, this is the equation for this one. Then I say, okay, for the second cell, which is this one, and the order doesn't really matter, but the observed number is 18. The expected number is 21.08. So again, I can fill out the equation, and I do the same for the 2 other cells. Then I sum up these 4 numbers, and I get a chi-squared value of 21.56. Then, based on my chi-squared value, I can find my p-value, and the p-value is really what we are looking for in a statistical analysis, because when we have the p-value, we can judge whether this is statistically significant or not. But to find a p-value, there's one more small step we need to take. We need to figure out the degrees of freedom. And the general formula is this, where m is the number of rows in the table we have used for data collection, and n is the number of columns. So, and since we have 2 rows and 2 columns, then we end up with a degree of freedom of 1 for this little test here. And this is then a table, or part of a table, that shows how to, based on your chi-squared value, how to then figure out your p-value. So the numbers that we have down here are chi-squared values, and what we have up here is then the p-values that go with this chi-squared value. This also means that for our chi-squared value, which was pretty high, it was way, we can actually not even see the number, it was higher than 6.6, right? So this also means that our p-value will be even less than 0.01. And what we do is that, or it's been decided that whenever the p-value is lower than 0.05, then it is statistically significant. And sort of the rule of thumb is that if p is low, null gotta go. So if you get a p-value lower than 0.05, you need to reject your null hypothesis and instead keep your alternative hypothesis. Yes, so this is basically just a sum up. For a chi-squared test with a degree of freedom of 1, a value greater of 3.841 is required for the result to be statistically significant, meaning that their p-value is smaller than 0.05. And the value, the chi-squared value that we calculated is 21.56, so it's way above this number up here, which also means that we have a p-value smaller than 0.01, which means that there is less than 1% probability that the results we see are just caused by chance. This means that the difference between the observed and the expected frequencies are statistically significant. And like I just told you, we reject the null hypothesis, so we keep the alternative hypothesis, which means that there is a statistically significant difference between observed and expected frequencies, which means that they are, these two species, associated in some way. And what we can then do is that based on the data, we can go back, we can have a look at our data, and we can say, okay, are they typically not growing in the same area? Then there's probably a negative association between them. Or are they usually present in the same area? Then there is a positive association. But simply based on the test, we can only say that there is an association, and then we have to take a closer look at the data to see what the association is, what type of association it might be. Yeah, I just also want to tell you that there is a very good example of how to calculate this on BioNinja, so you can use that also for figuring out how to do this. And you will be handing in a report based on this. And this is what should be in the report: short introduction, and you will be answering these 2 research questions. What is the size of the population of species A in this site or this area? And what is the distribution of species A associated, or is the distribution of species A associated with the distribution of species B? And you decide yourself which species you want to work with, right? So go out, observe the area that you want to work with, and then you decide which species to work with. Then in the report, you also need a list of materials, methodology, data presentation, of course, this data analysis that I just talked you through, a discussion. And in the discussion, you should discuss strengths and weaknesses of the investigation, such as the limitations of the data and possible sources of error. And of course, you should also have a conclusion where you state the answers to the research questions. Bye for now.